Hi, Mr. Myers here. In this video tutorial, we're going to look at the effects of volume, temperature, and pressure on gases and what their relationships are with one another. We'll start off with volume. Volume is defined as the amount of space that a substance occupies, and we measure it in milliliters, in milliliters or in liters. Remember the other day we talked about matter and said that matter is stuff or anything that has mass and take up space. And so the space here is referring to the volume. Any conversions that you might come across, just realize that we have milliliters to liters right there. Also keep in mind that 1 milliliter is equal to 1 cubic centimeter. In terms of pressure, pressure here is the force that is created when particles collide. Okay, so it's force due to collisions of particles. I referred in class, and so that pressure is equal to force divided by area. And so we'll see what kind of relationship that has if we move particles closer together, what happens to the collisions. So we'll see that later. But again, it's the force due to collisions of particles. So the collisions is key. Pressure is measured in atmospheres, kilopascals, or millimeters of mercury. And these below are the conversion factors. So if you have, say, 2 atmospheres, then we'd multiply it by the conversion factor to get millimeters of mercury. 760 millimeters of mercury for every 1 atmosphere. And then this would be, if my math is right, 1520 millimeters of mercury. So that's how we would work with those conversions. Now you've experienced pressure before when you've opened up a pop can. So say you've got a soda can here, and here's the little tab, and you open it up, and because it has carbon dioxide inside of the can, you know, if you shake it up or whatnot, it's going to be under pressure. The particles have been moving around quite a bit. They're bumping into each other. So when you open up that can, we have a release of that gas, and the gas has been under pressure. So as particles bump into each other in the walls of the can, creating that force. Now, the atmosphere, speaking of the atmosphere, it's also made up of gases and exerts a pressure on every object called atmospheric or barometric pressure. So atmospheric or barometric. If you're watching the weather forecast and they talk about, well, the barometer's holding steady here at 29.88 inches of mercury, then that's okay. If they're like, oh, hey, the barometer reads the pressure is falling, usually that's indicative of some weather event taking place, like rain or snow, for instance. So next time you watch the weather on the news, if that's still a thing, take a look, take a listen. All right, moving on then, temperature. So temperature is unique. And in the next class period, we'll talk about temperature versus heat. But for now, we need to understand what is temperature. And as it says here, it's an average kinetic energy of the particles. In other words, how fast are the particles in a substance moving? Now, we typically use a scale called the Celsius scale to measure or record these temperature values. And the Celsius scale is based on the ideal boiling point of 100 degrees Celsius and the ideal freezing point of water at 0 degrees Celsius. It's relevant because it's a useful scale for us. And here in America, we use Fahrenheit, but in the science community and most other countries throughout the world, we use the Celsius scale. So the Celsius scale, it's useful as many of our daily activities fall within this range. And as I said, it's commonly accepted around the world. See, though, there's a problem with the Celsius scale here, is that if you go below 0 degrees Celsius, we get a negative temperature. And since temperature is defined as the kinetic energy, or how fast these particles are moving, it makes little sense to have negative numbers, which would imply that the particles move less than 0. So the Kelvin scale solves this problem for us, because at 0 Kelvin, this is where all motion stops. We call this absolute 0. So all motion stops, nothing goes on there. And that's equivalent to negative 273 degrees Celsius. So this idea of a kinetic energy and particles moving and how fast they're moving, just the fact that there's movement means that we need a positive value to indicate that, because a negative value would indicate that we're going slower than stopped. How is that possible? How can we go slower than stopped? Ponder that if you need to. Okay. Now the conversion factor here, which I just covered up with my writing, says that degrees of Celsius plus 273 is equal to the temperature value in Kelvin. We can see that if we're at negative 273 degrees Celsius and we add 273, we get 0 Kelvin, which is absolute 0. Or if we're at 0 degrees Celsius and we add 273, we get 273, and so on. Now, to see the connection between temperature, pressure, and volume for gases, we can use some simple experiences that we've had. So we're going to look at 3 different scenarios, but in the process, we're going to see what is the relationship between each of these variables: pressure, temperature, and volume. So let's look at the relationship between pressure and temperature while volume is held constant. Remember, temperature is kinetic energy. So if, let's say, we increase the temperature, that means the particles are moving faster. If the particles move faster, they hit each other. They collide with each other with more force. So increase of temperature means increased collision of particles, which means there's more force associated with that. And remember that pressure is force divided by area. So if we increase the temperature, we're increasing the pressure proportionally. It's a direct relationship. And so graphically, we would see something like this, where pressure is on our y-axis and temperature is on our x-axis. And temperature must be in Kelvin. So say we're keeping this volume constant. We increase the temperature. What would happen to, let's say we have a balloon, okay, with some helium inside. Now go to the party store, get helium balloons, and so this is what we have. So in this scenario, we know the volume does not change. Okay, so volume, no change. So if we increase the temperature, then the particles are going to be moving faster throughout, and they're going to collide with the walls of the balloon on the inside and with each other and create more pressure because there's increased collision, increased force. So temperature increases, particles move faster, they collide more, so the pressure would increase. So from that reasoning, we can make the statement that it's a direct proportional relationship. So that means if we double the temperature, then we must also double the pressure. It's a direct relationship. How about constant temperature? So now pressure and volume. When the volume increases from one container to a larger container, the pressure is going to decrease. The idea here is, say we have 5 particles that we can kind of see there. And they're pretty close together. So if they're close together, they're going to collide more frequently. But if we increase the volume, those particles spread out, which means they come into contact less often. So there's fewer collisions, which means we have a lower pressure as well. This is an inverse relationship. Graphically, we would see it in this manner. Pressure against volume, we see a negative slope. As the volume increases, the pressure decreases. Okay, so that means if we were to double the volume, we would expect that our pressure would go down in half. All right. Now for a constant pressure. This means we're associating just volume and temperature. In this scenario, let's say we have our balloon again, and we have some helium particles in here. The idea is if we increase the temperature, then the particles move faster. If they're moving around faster, but we keep pressure constant, they're going to collide, but we want to make sure that that pressure doesn't increase. And so the way to fix this is to increase the size of the balloon. So if I change my color here to show you, the balloon is going to get bigger to accommodate those particles moving faster. So it's a direct linear relationship. And graphically, it looks similar to the first graph we had, this time volume against temperature in Kelvin. We have a direct linear relationship with a positive slope. Okay, so that means if we were to double the temperature, we would also have to double the volume to accommodate that. So your goal from here on out is to, there we go, colon there. Your goal is to understand the concepts here that have been presented. Okay, like what is pressure, what is volume, and what is temperature, and what happens when we keep one of them constant and change the others. What is their relationship based upon the particles and how the particles behave? So particle behavior, that's the key there. Should be behavior. Okay, so that's it for this tutorial video.